If you haven't had your morning cup of coffee, wake up now. It's time for the one, the only, Matthew Gershoff. Gershoff train, all aboard.
All right. Now that we're in the station, we got work to do. Topic today, this morning, is going to be really information theory. We're going to talk about entropy, and I'm not going to lie, it's going to be a little rough. It's not going to be the easiest thing. We're probably not the type of thing that we're going to grok everything in the 45, 50 minutes or so. But I first stumbled upon entropy back in 2000. I was working at a startup in New York during .com 1. And I was building a diagnostic system for customers to kind of diagnose problems they have with their products. And the objective was to give them, to ask diagnostic questions, but as few as possible, and to ask the most informative questions so that we can resolve their problem sooner rather than later. And so it's very much like a doctor. And they try to ask the fewest number of questions or do the fewest number of tests in order to sort of diagnose what the issue is. And in a very real way, that's our job as analysts. And that sounds like a loose analogy, and we always use, often there's a lot of loose analogies, but actually it's not loose, and we're gonna make a link between questions and information. And in this session, we're actually going to define information. So we're actually, instead of talking about it in a general sense, we're going to give a metric or a measure around it. And then we're going to use that measure to do our analysis and to do a little machine learning. Sound good? Okay. So who here has played the lottery? Raise your hand. Come on, up. Okay. Just out of curiosity, who here has lost playing the lottery? Okay. And just, has anyone won the lottery? Really?
Free ticket.
Oh, free ticket? Okay, but anyone won anyone won more than the equivalent of $1,000 or €1,000 or £1,000 or whatever? Nobody.
My wife got a car.
You what?
My wife got a car.
Oh, that's awesome. Right? That's surprising. Okay, so we've all lost. Everyone who's played the lottery has lost, right? Trust me, we're going to ramp it up. So just enjoy the simple stuff right now. So we've all lost the lottery. Now, what happens when you lose? Right? Do you go, oh my God, I lost the lottery? That's amazing, right? It's like I can't believe it. And then you're like, oh, I'm going to go run, and tonight I can't wait to buy people drinks and tell them the story. Look at this. This is a losing lottery ticket. Can you believe it? Right? No one does that, right? Because it's not interesting. You're more like this. If someone were to come up to you and start talking about how they lost the lottery, you don't care. But why don't you care, right? Losing the lottery, it's not surprising. Right? Again, I'm telling you, we're going to ramp it up. So if this seems obvious, good. It's not interesting, right? You go tell someone you lost the lottery. We've all lost the lottery, and you expect to lose the lottery. It's not informative, right? This is important. No, it's not informative. You can afterwards. When we talk at the end, you can challenge me. I'm totally good with it for an argument. Winning is surprising. It is interesting, and it is informative, right? It's news, right? News is something that's new and you haven't heard before. Proper news, okay? So if an event is predictable, it's not informative, right? So if we can predict it, we already know it, we already have a high prior belief that we're going to see the event, and we see the event, it's not informative, okay? If something is not predictable, it is informative. Okay, so we're trying to make a link between prediction and information here. And there is a direct link. So what is information? right? And so Doug yesterday was talking about PCA, and I noticed him saying, I was talking about the variance along the variance, the orthogonal rotation, and he mentioned giving you a sense of how much information was in the variable. But what are we really talking about when we say information, right? What is it really? And I would say, you might think data is information, but I would argue that it actually isn't. Okay, so data is not information. Does anyone know who this rather handsome gentleman is? This guy, Zoli? Anyone? Go ahead. You can just throw out a guess. Okay, this is Claude Shannon. Okay, Claude Shannon is the inventor of information theory. Okay. And when I was procrastinating writing this report, and I was sort of ADDing it, I was trying to think who would play Claude Shannon, right? So it was like kind of working, but not really. And so I tweeted this. I think Ian McKellen would do a pretty good job. Anyway, so I tweeted that, and like instantly, some guy who wrote a biography of Claude Shannon was like, yes, and retweeted it. So I'm sure he would love to have Ian McKellen play this guy. Anyway, he studied at MIT. Oh, wait a minute. No, that's not the right guy. That's another person who studied at MIT. Okay, that's it. I got it right. Okay, he studied at MIT. And in 1948, when he was at Bell Labs, he published this paper called The Mathematical Theory of Communication. And Bell Labs, if for the folks here who don't know, is like the American telephone company, and they did actually a lot of research. That's actually interesting. Now we think of like Google and Facebook, Yandex. Who am I forgetting here? What? Yeah. Okay. Whomever. We think of them as sort of like the leaders of technology, but actually a lot of the advancement in statistics and machine learning and information theory, those old school companies like IBM, you can't believe how much work was done there. Same with Bell Labs, unbelievable amount of research. So actually this idea of private companies generating a lot of research really isn't that new. Anyway, what he was trying to study, or he was trying to come up with, was how to send messages over noisy channels, right? So back in the day, and even now, there's like a lot of noise that can come in when you're trying to send a message, and so you want to encode the message in such a way that you can recover it, right? So it's over a noisy channel. So in so doing, he came up with this definition of information, which is it's the amount of information content of data or a message is equal to the smallest average encoding, right? So there's this idea of information is related to compression, right? So we have a big chunk of data, we have all this binary data, and can we represent it while still retaining the original source in a smaller size, okay? So the more predictable, the more compression, the less information, okay? So the more predictable, the more compressible, less information. So Shannon's entropy, so here's where we're going to introduce the term, is a measure of how unpredictable our data is, right? And as analysts, we're interested in making predictions often. So there's going to be a deep relationship between this, between information, and it's actually, he coined it, he called it entropy because it's actually related in a very deep way to Boltzmann's entropy in thermodynamics, right? So that's like how many possible configurations of the state that matter can be in, and that higher entropy. And here it's how many possible states and the configuration of our data, of our information. So it's directly related. Just a reminder, like in computers, and data is usually binary data, so it's in bits, right? So data is in 0, 1s, okay? It seems obvious, but this is actually, we're going to talk a lot about this. So entropy can be thought of as the minimum number, on average, of bits to fully encode our data. It's the minimum number, okay? So, again, related to this idea of compression. Or equivalently, and this is where we should start, get a little excited. This is amazing. There's so many amazing things that this opens up. And I know I'm not the best messenger for this, but trust me, this is so unbelievable. Entropy is also the minimum number of questions that we would need to ask to identify all the possible values in the data, okay? So I know that that's super confusing, so we're going to spend like the next 15 minutes or so going into this in a little bit of detail, and so hopefully when we walk out of here, you're going to have a good understanding of that. So we're going to take a little break, and we're going to play a game of 20 questions, really 4 questions. Okay, I'm thinking of a letter, right? And the game is to ask me questions in such a way that you ask the fewest number of questions to identify what letter I'm thinking of, right? So there's 4 letters. Is everyone familiar with, anyone not familiar with the game of 20 questions? Okay. So the first approach, and all the computer scientists here will be aware of this, it's like a binary search, right? We're going to ask one question. The first question is going to be, is it C or D, right? Because I'm going to split. Right? So if it's no, when you ask me, is it C or D, I'm going to say no. You're going to ask another question, and you're going to say, is it B? You could say, is it A? If it's not B, you know it's A. And if it is B, it's B. And the same thing. If it is C or D, then you're going to ask, is it D? Right? And so now we're going to be able to identify, if you play this strategy, you're always going to be able to identify the letter in 2 questions. Right? We could have done it naively. Is it A? Is it B? Is it C? Is it D? Or in any order. We could have gone up to 4 questions. But here, we're going to guarantee that we're going to be able to identify any element in 2 questions. Now, what if we swapped zeros and ones for the yes and nos? Right? We can do that. Then, if we walk the tree, we can recode our letters into bits. Right? So there's this direct relationship between our decision tree, our questions, and bits, right? Our binary data. So this is kind of amazing fact number 1. The number of bits is equal to yes/no questions, these true or false questions, right? There's a direct relationship. So you can start thinking about information or data is related to the number of questions you would need to ask of it in order to identify any possible element within the data. So what's even more amazing, though, is that we can use the prior distribution. So what if you knew beforehand, before we play the game, and I said, I'm going to pick these letters from this distribution. So I'm going to pick A. I'm going to be thinking of A 50% of the time, B 25% of the time, and C and D 12.5% of the time. And now you know that. Now the question is, should you play that same strategy? Right? You're guaranteed you could do it in 2 questions, guaranteed. But you'd have to play 2 all the time. So let's see if there's a different strategy, right? Where maybe we can do it in less than 2 questions. Okay? So now, because A is the most frequent frequent letter, I'm going to ask that first. Is it A? Yes? Great, it's A. No. Well, then is it B? Because that's the next most likely letter. Okay? Is it yes? Great. No? I can ask, is it C or D? Doesn't matter. And then I'll identify. Okay? So here I have 3 questions that I've asked, up to 3 questions. And here's the encoding, so it's different now. So instead of, it's unequal. I don't actually have the same number of bits, because before, I always asked 2 questions. But here, these bits, the data, is representing these questions. Right? I have to ask 3 questions, so I have 3 bits for C and D. But I only have to ask 1 question to identify A. So we wanted to know what's the average number of questions. So if we were to play this game repeatedly, on average, how many questions would you have to ask me? And remember, like the doctor, it's just a diagnosis. We're trying to diagnose the problem, which is what we're trying to do as analysts, right? And so we want to do it as efficiently as possible, right? We want to do it in the minimum number of questions. So this is the average is just a weighted average, the number of questions times how often it's that letter, okay? So in our case, A, 50% times 1, because we only asked one question, B, 0.25 times 2, and C and D, 1.25 times 3, okay? But that's kind of amazing, because we've only asked 1.75 questions on average. So can we do better? Yeah, we just did, okay? So what's amazing is that what questions we want to ask, right? Conversely, what data we want to inspect in order to make predictions about another bit of data is going to be dependent upon the prior probabilities, right? Or the distribution of our data, okay? So this is going to be Tim Wilson's favorite chart here. But actually, I think it's kind of useful here. So the more predictable the data, the fewer questions or bits needed. This is kind of key. So in our first game, when we thought that the letters, or we assumed the letters were uniformly distributed, were equally distributed, we had to ask 2 questions. There was no way of getting around it, right? The minimum was 2, right? But in this other case, when we had an uneven distribution, we didn't need to ask as many questions, right? Because in a way, there's less information in asking those questions. We needed less. We can compress it. And if all of the data was one letter, if I said before we started playing the game, A 100% of the time, you wouldn't ask me anything. You'd say it's A. So if all the data is perfectly predictable, right, it's all the same, there's no information. There's no, you don't have to ask any questions. Okay, so it's math time. So the information content for an event, like of the letter, okay, is log base 2 times the probability of the event, okay? So we have the probability of the event. So like in our case before, like A in our game is 50%, so we would just put 0.5 here. And it's log base 2. I'm not going to get into log. We can go into other time, but afterwards. But it's just because it's in bit, so it's in binary. So it's base 2. So entropy, and I can't overstate how significant this is in machine learning. Like almost every single machine learning algorithm, this pops up, actually behind the scenes if you derive the algorithms. And so this is really sort of fundamental. Okay, so let's go through this. So all we're going to do, it's just algebra. Okay, we're going to calculate a weighted average, right, of the information. So there's the probability of the event, right, and then there's the information content of the event. Okay. Now I know Doug, you're here, right? Yeah, he's back there and he's thinking, Gershoff, that looks a lot like that calculation you did for the number of questions that we just did before. A very similar looking equation. Okay, let's see if Doug has any intuition here. So let's go and calculate the entropy. Before we calculated the number of questions needed, and we said it was 1.75. Now let's calculate the entropy, right, of our distribution in that game we just played. Okay? So first, this is just algebra. We're going to calculate the log of the probabilities. Okay? And so we have -1, -2, -3, -3. And now we're going to calculate the entropy. And again, it's not that complicated. So our A is 0.5 times -1. So the probability of A was a half, and the log of 0.5 is -1. B, C, D, right? But that's 1.75, which is exactly the same as the average number of questions that we had to ask to play our game before. Doug, you were right. Doug's crushing it. So Doug was absolutely right that it is very similar, and in fact, it is the same thing. So entropy, right, this very profound and deep measure of information content, we just showed is equal to the number of bits required, the minimum number of bits required to encode your data, which is equal to the number of questions you would have to ask in order to identify. And this is totally amazing, because it's an exact mapping between information content and the minimum number of bits required. Okay, now I see everyone's faces, and you're like, who cares? What can I do with it? I see you. That's fine, whatever. Some people don't get it. I think this is totally amazing, and in fact, it's not just in analytics. It's this way of thinking about it. I mean, think about it. What's more interesting, Paris, France, or Sour Lake, Texas? Right? And most people would say Paris. And if you think about it, why? Well, Paris exists in a multiple of states, right? There's so many statements you need to make to describe Paris, right? There's people wearing different clothing, there's so many different shops, there's different streets, there's the architecture. You would need so many bits. Think about how many bits you would need to encode Paris. It's not that compressible. Whereas Sour Lake, Texas, it used to have a sour lake, apparently, Sulphur Lake. That's gone, and now it's got an oil lake because of some oil disaster 100 years ago, and they never cleaned it up. That's it. I've just described it in like 3 statements. So just think about it. This totally changed how I look at the world. It's amazing. So you can just, with everything, it starts, oh, well, of course Paris is more interesting. It's more information. It's less compressible. It has higher entropy, right? You want to live a life that maximizes its entropy, your entropy. Okay? Little terrible philosophy for me. Okay, so now let's get to what you want to do with it. And we're just going to go over this really quickly. We're going to talk about information gain. Does anyone have any questions? I can stop for a second. Does anyone have any questions? No? Not impressed? All right. So information gain. So we're going to, why this can be, one way this can be useful, and we use this in our software in Conductrics. We had the problem of, we do sort of predictive, we blend A/B testing with machine learning, and we do sort of adaptive predictive modeling, right, for companies. And several years ago, I realized it was really hard for the clients to interpret the results, and so that was really important. And so I use entropy, like an understanding of entropy, to sort of build your own tools to have it so that we can recast our predictive models into these decision trees. And we use this. So this is like an actual thing that gets just used in practice. It's super powerful. So anyway, so the idea is that we're going to turn prediction or predictive targeting into a problem of reducing entropy. So information gain, it's a key idea in decision trees. And I used to think, and I think Tim might talk about this a little bit. I used to think that regression, like linear OLS, these squares, was sort of like the good first entry into predictive learning, predictive targeting. But now I think actually decision trees are, because you actually need a lot less math. All you need is this idea of entropy, and that's basically it. And you can build your own decision trees. And this idea, I think, first came from the ID3 algorithm. I should cite that, but it's the ID3, and I think maybe Shade even before that. But this idea of information content or conditional information content is behind this. And it's the type of thing you can kind of do by hand. And I actually recommend, mucking about with this. Maybe I'll put up a Google Doc. And you can just do this by hand or in a spreadsheet just to get a feel for it. Because it's just algebra, right? It's nothing that, there's no calculus, there's no linear algebra. It's just stuff that you can do by hand. So information gain. So we have the entropy of our target variable, okay? And that, remember, that's a measure of uncertainty or a measure of dispersion or a measure of impurity in a way. And in this case, just think of X was like when we were, our letters, right? But in the marketing problem, you know, we don't get to ask the customer, hey, are you a converter or not? Are you going to convert or not? And then I'm going to tell you, you don't have access to that. But you do maybe have access to other data about them, which you can use to reduce your uncertainty about whether or not they're a converter or not. And that's what this is. That's this conditional entropy, and we're going to go through that. But it's you can almost think about information gain as a way to help you automate your SQL selects, right? It's actually, what we're going to be doing is partitioning the data in very much the same way as a where statement, right? We're going to have these hard subsets, right? Which is what you might do, when you're doing your queries in BigQuery or whatever. So you can use this. So here's our example data, and you obviously would never build a model on 12 data points, but I just wanted to make it so that we can see the data. So we have 50-50 conversion, right? So we have half didn't convert and half did. And then we have whether they were on a Windows machine or not, right? And so yes, no, were they Windows, and whether they were on a mobile device or not. Okay? Don't worry, this is just dummy data, but this is just to be illustrative. So here's some summary statistics. Okay? So if you were on the Windows, yes, 50-50, so half the people were on Windows and half the people weren't. So the coverage is 50-50 there. The conversion rate on Windows is 83%. Oh, okay, that's a good indication. And the conversion rate is only 17% for if you're not on Windows. And I went and I just calculated the entropy, just like what we did before. But I calculated, so the entropy of the conversion rate, just like we did the entropy of the letters, the same thing, but I just subsetted it. So I calculated the entropy just on the users who had Windows yes, and then just on the users who had Windows no. So I just did that same calculation we did for the letters, but I did it for conversion for those two different subsets. Okay, is that clear? So I just split the data, yes, calculate the entropy for conversion. Split the data for Windows no, calculate the entropy of conversion. And then I did the same thing for mobile. Okay? So mobile, yes, no. The coverage is there's more people who aren't on mobile, 58%, and 42% yes, we're on mobile. And then the conversion rate for mobile was 60%, and not mobile was 43%. And here are the entropies. And notice this is very close to 1. Okay? And at 50-50, the entropy, this is actually 9.89 or something, but the entropy is 1. So the maximum entropy, and this is actually related to the maximum variance of a binary variable, and that was part of the question, the podcast on Tim's, the Power Hour, related to the, it's very much related to the maximum variance, okay? So this you can do by hand. You can do this in SQL, or you can do this in Excel, or whatever. Nothing difficult, just algebra and some queries. Okay. Anyone have a guess which one is the most informative? I made it easy, but okay. So now we're going to calculate the information gain. So it's just a weighted average of the entropies. So for Windows, yes or no, for that variable, it's 0.5, so half the people were on Windows, and the other half were not. And it was symmetrical in this case, so the entropy of yes is 0.65, Remember, 1 is the upper bound, 0 is the lower bound for when you have just 2 events. And so the information gain, so the reduction in entropy is 0.35. So we're reducing the impurity, we're reducing the uncertainty of conversion. If we know Windows, if we use Windows to condition. And now the gain for mobile, yes, well, 42% of the users had a mobile device, and the entropy of the conversion rate for those users was 0.44. No, 58%, and very high entropy, because it was almost close to 50% conversion rate, which is the same as the overall. So the gain is 0.24. So here, our algorithm, which you could write a loop, or is just us, as we're doing the analysis, you would take windows, okay? And then we're going to split the data by windows, right? And this is the type, like I said, you could actually just do this with your SQL statements. But we can build a tree. So the way the tree building works is a recursive algorithm, is that you calculate the overall conversion rate, which is 50-50, right? So that's what the overall conversion rate, and that's if we didn't have any additional information about our users, right? So your guess is half the time they're going to convert, half the time they're not going to convert. And I don't have any other information. That's the best I can do, okay? Then we're going to split the tree, and we're going to create leaf nodes. And in your mind, just think of a query or a select statement, and this is just all the data with a where condition, where Windows equals no, and then this is all the data with a where condition, where Windows is equal to yes. So the tree, underneath the tree in each node, you can also just in your mind think of a little SQL statement behind it, and it's just a select. Select the data where this statement is true, okay? And as we see, one other thing to notice is that notice the probabilities of the conversion, the distribution, is not equal. Here, it was equal, right? This is maximal entropy up here. But here, notice, it's less, it's more pure, it's less impure, right? We have more certainty. We have greater predictive ability in each one of these nodes, right? So we've converted this entropy question where we're trying to reduce the entropy of our target value, variable, with a prediction problem. It's sort of the dual of it, right? I think that's amazing. So here's the little algorithm that you can play around with the data for mobile, or any data that you have. And I'm happy to take questions. You can ping me on email if you have any questions. So we're now going to repeat the same process for each leaf node, right? So we're going to take all the data with the no select, with Windows equals no, and we're going to do the exact same thing we did before. We're going to calculate our summary statistics, and we're going to say, when Windows is no, we're going to calculate the conditional entropy of mobile, yes and no, and see whether or not we want to include it. And the same with yes, and you keep doing it. And you do it until there's no more variables to check. And then you also have these other thresholds that you would include in the algorithm, which is, like, this is ridiculous. There's like 12 data points, so you'd never really want to split it. But you want to have a constraint on the node size, and that's going to be kind of a business decision. It's like, what's a meaningful segment at the end? If there's only 50 people in it, would you want to try to split it again? No, probably not. If there's 10,000, yes, that's probably fine to keep trying to split. The information gain, because notice we were calculating those information gain, that going to get smaller and smaller as we iteratively keep adding in new data. Because remember, we're greedily grabbing the data based upon the one that reduces the entropy the most. So that means at the margin, each additional data point, each additional targeting feature has less and less capacity to reduce the uncertainty, which means it has less and less efficacy with respect to predicting at the margin. And we also might want to limit the tree depth. So you might want to have a limit on how many features you want to include in the model. And these are all parameters that you set, and it's related to overfitting. Because what we don't want to do is just sort of map the data, and then when we try to use it in the real world, we've just modeled noise, and we haven't really modeled the structure. But what I think is amazing about this is that, I mean, really, unlike regression, which, you know, is totally worth the effort, this is something you can actually just, you can know the math behind it, because it's just algebra, really, but it's actually much more than that. And you can do it by hand just to get a flavor of it. And so even if you're not going to be building these algorithms, it could be useful in helping you guide your analysis, or even just understanding how it works. So if someone's talking about decision trees, you know, oh yeah, okay, we're minimizing entropy, or we're using information gain. One other thing about information gain is it's also known as the Kullback-Leibler divergence. And it's also used, there's a whole machine learning approach called minimum description length, which is not quite the dual, but very similar to Bayesian modeling. So there's a whole world, there's various worlds that you can explore when you start with entropy. It just sort of opens up a whole new world, I think. So Doug the other day asked who loves data, and he asked people to raise their hands. And I thought about it. I was like, you know what, Doug? I don't love data. I don't hate data, but I don't love it. I love information. And I hope after this, you do too. And I hope it's like, from now on, you think about information and not data. Who cares about data? Data is only good with respect to that equation, right? And that's the key thing, is the information content in the data. And with that, thank you very much.
A round of applause!
Thank you.